Okay. All right. So we've got this idea of displacement, velocity, and acceleration, but that's not the only places where we might come across having to use differentiation. So recently, we've been looking at electricity and inductance, and actually, if you look at this equation over here, or this set of equations to do with the induced EMF, um, we actually see, well, you might have noticed now, we've got some notation that reminds us of our differentiation notation. So, for example, we've got this equation, and we've also got this equation over here, E is equal to minus L di dt. So this d phi over dt, and here di over dt. So this would be the rate of change of phi, which is our magnetic flux, as time changes. And here, if you remember, it's di dt. If we have an inductor, how the current varies with time, right? So di dt, the rate of change of current. Okay, so let's actually look at an example like this. So here I've got a question where it says the magnetic flux through a coil with 500 turns changes with time as described by phi is equal to 5t squared plus 3t to the 4. So it's asking what is the instantaneous induced EMF when t is equal to 2 seconds. So if we have a look, induced EMF, one of those equations we just saw, is given over here. This is in your formula sheet. E is equal to minus n d phi over dt. Well, here, that's what we need to know. We know, let's see from the question what we know. We know n is 500, and we have an expression for phi, that magnetic flux. But we need d phi dt. So actually, we need to know how quickly the flux is changing with time. So we need to differentiate. So let's find out a general expression for d phi dt by differentiating. So let's differentiate this. So power goes down by 1, 5t to the 1, multiplied by the old power, times by 2. Let's do the same thing for the second term, 3t cubed, and then times by 4. So we've got 10t plus 12t cubed. So we now know what our d phi over dt is. However, we want to know what this is going to be when t is equal to 2 seconds. So when t equals 2, d phi over dt, let's substitute in t equals 2, is 10 times 2 plus 12 times 2 cubed. Again, you can use your calculator here to help you. 10 times 2 is 20. 12 times 2 cubed, that's 12 times 8 is 96. So d phi over dt is 116. Okay. So d phi dt is 116. We actually want the induced EMF, don't we, at time equals 2. So now we know what d phi dt is at time equals 2. We can put it into our equation. So E is equal to minus n d phi dt. Well, we now know that d phi dt is 116 and n is 500. So E is equal to minus 500 times 116. All right, and again, putting that into our calculators, 500 times 116 gives us minus 58,000 volts. So our EMF here is 58 kilovolts, or minus 58 kilovolts. So again, minus because it's like opposing the change in the magnetic field. But if you put down minus 58,000 or 58,000, you should get the marks in this instance. Okay, so again, just seeing what we did there, we used our equation, but we had to differentiate phi with respect to t, and then we had to use the fact that we wanted t equals 2 in our answer. Okay, in the next couple of videos, I'll look at some similar exam questions from the sample assessment papers, but hopefully by the end of all this, you'll feel much more confident in how to use differentiation for engineering.